You are standing on a brand new concrete pier. The salt spray hits your face. The gray slab under your feet feels permanent, unbreakable. It is not. Give this pier 50 years in the open sea, and it will be spalling and crumbling into the waves beneath your feet. The steel rods hidden inside it rust and swell. Salt water works into every hairline crack. The strongest marine concrete we can pour today rarely outlives the engineer who designed it. Now travel to the Bay of Naples in southern Italy and look beneath the surface. There, resting on the seafloor, stand walls built by Roman hands 2,000 years ago. At a sunken town called Baiae, whole breakwaters and harbor walls are still there, still solid, still holding their shape after 20 centuries underwater. By every rule in a modern engineering textbook, they should be gone, ground into sand long ago. Instead, they may be stronger now than the day they were poured. And the secret starts at a volcano. The volcano is Vesuvius, looming over the bay, and scattered across its slopes lies a dull, ordinary-looking gray powder. The Romans called it pulvis Putiolanus, the dust of Puteoli, named for the town near Naples where they dug it. Today, we call it pozzolana. It is volcanic ash. To a Roman engineer, this dull gray grit was one of the most valuable building materials in the entire empire. And here is why. Picture ordinary mortar, just lime, sand, and water. It hardens by drying out, so it needs open air to set. Pour that ordinary mortar into the sea, and it fails at once. It clouds, it dissolves, and it drifts away in the current, completely useless. But blend the volcanic ash into the mix, add seawater, and the rules break. Instead of falling apart, it sets, rock hard, fully submerged. Chemists have a name for this now, a hydraulic reaction. A material that hardens by reacting with water, rather than by drying out in the air. A Roman architect named Vitruvius even wrote it down. Mix this dust with lime and rubble, he said, and it will set fast underwater and defy the pounding of the waves. The Romans could not have explained a single molecule of it. They simply knew that it worked. And with it, they set out to do something no civilization had ever done. You already know their concrete on dry land. The dome of the Pantheon in Rome, poured 2,000 years ago, is still the largest unreinforced concrete dome in the world. But the sea was a far crueler test. To understand why it lasts so long, we have to go smaller, much smaller, down inside the concrete itself. In ordinary modern concrete, seawater is the enemy. It creeps into the pores, it corrodes the steel, it splits the stone apart from within. In the Roman mixture, seawater does the exact opposite. It is not the attacker. It is one of the ingredients. It seeps into the microscopic gaps and reacts with the leftover volcanic ash and lime that never fully set the first time. And slowly, over years, over decades, it begins to grow crystals. The crystals have a name, a luminous tobermorite. In nature, they are rare and difficult to make. Inside these walls, the sea grows them for free. They grow long and flat, like tiny interlocking plates, threading through the concrete and binding it tighter with every passing year. So when a crack finally opens, seawater floods in and grows fresh crystals right across the gap, and the crack seals itself shut. It is, in a very real sense, a self-healing stone. Every wave that should have broken the wall instead helped to rebuild it. We only learned this recently. Scientists drilled cylinder-shaped cores out of the ancient piers, put them under microscopes, and found the crystals still slowly growing. Now, hand a material like that to an empire obsessed with building, and watch what happens to the map of the world. For every civilization before Rome, the coastline set the rules. You could only build a harbor where nature had already carved out a sheltered bay. No bay meant no safe port. No safe port meant no trade, no fleet, no power. Geography alone decided who ruled the sea. Roman concrete tore that rule apart. Now, if there was only open water where they wanted a harbor, they simply manufactured one from scratch. Here is the trick. Carpenters built an enormous double-walled wooden box called a caisson and lowered it into the shallows. Into that box, they packed the volcanic mortar and rough chunks of rock, layer after layer. Sealed inside the wooden form, deep underwater, the mixture hardened into a single artificial boulder the size of a small house. One block after another, they marched breakwaters and piers straight out into the open waves, along coastlines that had never offered a moment of shelter. The most astonishing example sits on the coast of what is now Israel. There, King Herod built Caesarea, a vast, deep-water harbor on a flat, open shore with no natural bay at all. The volcanic ash for a job like that was dug in Italy and carried across the Mediterranean by the shipload to raise a port 1,000 miles from the volcano that made it possible. And those harbors became the arteries of the ancient world. Grain, oil, wine, marble, and soldiers, all flowing through ports that had been conjured out of empty sea. For centuries, more grain reached the city of Rome by sea than its own fields could ever grow. Close to 1 million people were fed through harbors like these. The Romans came to call the whole Mediterranean Mare Nostrum, our sea. And this humble gray volcanic dust is a large part of how it became theirs. Now, come back to our own century. We build with concrete on a scale the Romans could never have imagined. It is the most used material on Earth, after water, and most of it is a quiet disaster. To make modern cement, we roast limestone in giant kilns at around 1,500 degrees Celsius. That single process releases roughly 8% of all the carbon dioxide humanity produces, more than every airplane in the sky combined. And a modern seawall might last 50, maybe 100 years. The Roman harbors have already lasted 20 times longer, and they are still standing. And for all that cost, it is brittle. Our seawalls and coastal defenses crack, corrode, and fail, just as the rising ocean arrives to test them. So engineers have started to do something unusual. They have begun to study the ruins. In 2026, research teams are picking apart the Roman recipe, trying to rebuild its chemistry inside modern, low-carbon seawalls and coastal defenses. The appeal is obvious. The Roman mix is cured at far lower heat, so it takes far less energy to make. And it grows stronger in salt water instead of dying in it. Those are the exact two problems our own concrete cannot solve. There is something humbling in all of this. The people who mixed these walls are 2,000 years gone. Their empire crumbled into ruins long ago. They never once saw the tiny crystals growing in the dark. They died believing, at most, that they had built something that would last. But what they had actually built was something that would heal. And it is still down there, in the quiet water, stronger than the day it was poured. Waiting, patiently, for us to remember how they did it.